if you're ready, I would begin.
Please.
Perfect. So, good day, everybody. I can see that the participants are still increasing, but in the interest of giving as much time to Johannes for his presentation and also for us for our discussion at the end, I would start now. So I'd like to welcome you to today's webinar on climate smart biochar systems, and I hope you're all doing well today. I'd just like to give you a little bit of quick technical information before we begin. So all attendees, your microphones are muted and also your videos are switched off, and that will be until the discussion at the end of the webinar. And in the meantime, if you'd like to ask a question to Johannes, you can write it in the chat whilst he's giving his presentation. You can also use the chat if you're having any technical issues, and we will try and resolve those as well. And then during the discussion, you're welcome to use the raise your hand function so that we can mute your microphone and you can ask a question. The webinar is being recorded, and the recording along with the presentations will be available on the GBEP website. So now I'll just pass over to Michela Morese, who's the Executive Secretary of GBEP, and she's going to give us a brief background to the webinar. Over to you, Michela.
Thank you so much, Connie. Well, good afternoon and good morning to everyone, depending on where you are connected from. I would like to welcome you all to this webinar on climate smart biochar systems, and I would like to thank you all for your participation. I see the number of participants is slowly is growing, and I very much look forward to hearing the presentation of our keynote speaker today, Professor Johannes Lehmann from Cornell University. As you know, this webinar is organized by the Global Bioenergy Partnership as part of its program of work. For those of you who are not familiar with the Global Bioenergy Partnership, it is an international initiative that brings together 80 partners and observers all over the world, from all over the world, mainly governments and international organizations. As you may see from the slide on the screen, we, throughout the 14 years of our activities, we've been working a lot on sustainability, on GHG methodologies, and on capacity building. And in particular, we have developed a set of sustainability indicators to guide the sustainability assessment of bioenergy produced at the national level, with a view to guide policymakers in their informed policies. This specific webinar is organized in the context of the Working Group on Capacity Building, Activity Group 7, specifically on biogas. And it is the second webinar of a series of webinars focused on biochar. Connie, if you could, great. So the first webinar was organized a few weeks ago on the 7th of May. It was focused on the biochar systems for sustainable agriculture. Our keynote speaker was Professor David Chiaramonti from Polytechnic University of Turin, which is connected also today in this webinar. And the webinar of the 7th of May was focused on mainly the technological part of the production of biochar characteristics depending on the feedstock and the processes that are used. And then also it focused also on synergies between biochar systems and biogas produced from the anaerobic digestion of organic matter, as well as co-composting biochar with digestate to be used also as a fertilizer, as we know. This webinar of the 7th of May, as well as this one of today, was recorded, and the recording are available online. But now I would like to give the floor back to Constance Miller to give an overview of this webinar of today, the focus, and our keynote speaker. Annie, over to you.
Thanks, Michela. So as Michela just said, today's webinar, we will be discussing the opportunities and challenges of climate smart biochar systems. And our keynote speaker today is Professor Johannes Lehmann, who is the Liberty Hyde Bailey Professor of Soil Biogeochemistry and Soil Fertility Management at Cornell University. So welcome, Johannes. Johannes has over 20 years experience in the biogeochemistry of biochar and its sequestration in soil, as well as sustainable land management practices more generally. He's authored an impressive 250 journal publications and is a Thomas Reuther highly cited researcher. So we're very pleased that Johannes is here today to share his expertise with us. He'll be focusing on the agronomic aspects of biochar, specifically the crop yield responses to biochar application in different soils. And he will also discuss the potential of biochar for sequestering carbon as part of bioenergy-biochar systems. So I'd like to thank Johannes again for being with us here today, and I will pass him the floor for his presentation. Thanks, Johannes. Over to you.
Thank you, Connie, for this kind introduction. Thank you for inviting me, reaching out, Diana Michela, for the introduction. I'm really excited to be here with you today and in this interesting series of talks on biochar. And I will focus more on the soil part, as Connie mentioned, and look at it through the lens of climate smart agricultural soil management. The initial motivation for biochar came from Terra Preta, but not only from Terra Preta, but the most recent impetus can be credited to the rediscovery, one should say, of these remnants of Amerindian populations in the central Amazon that are featured large amounts of biochar type carbon that is remarkably old, several hundreds to several thousand years old, and had a lasting legacy effect on soil fertility, as you can see in these slides. But although the Amazonian Terra Preta are one of the more visible and impressive soils that bear this characteristic, they're by no means unique. You can find these kind of soils in all continents. Here an example from sub-Saharan Africa, Liberia, but also in Sierra Leone and Ghana. Can we find African soils that are now dubbed African dark earth soils that have several times more carbon, and notably 10 or more times greater biochar type carbon, accompanied with greater nutrient contents, especially phosphorus. So these features are extremely interesting because they seem not only to bear greater fertility, but also longer lasting fertility. In Africa, it was possible to study the agroecology, which wasn't really possible in the more archaeological soils in the central Amazon, because in Africa, many of these soils are actively managed and contribute proportionately a much greater, had a much greater contribution to food security than their spatial extent belies. And you see here 1% of the agricultural area in this village was covered by African dark earths, but about 25% of food consumption and household income could be credited to these soils. So what is biochar? Just a quick recap from what you undoubtedly heard in the last webinar and probably already know. Biochar is produced through anaerobic thermal conversion, starting at about 200 to 150 degrees. The charring process slowly sets in, and char is produced at about 300 degrees or 350 degrees onwards, with increasing aromaticity and odoring at higher temperature. In soils, one of the first very interesting findings from these legacy effects of Amerindian Terra Preta soils was that consistently these soils with high biochar contents had greater cation exchange capacity. So that's a very desirable feature, that soils retain cations such as calcium and magnesium and potassium. And you see that this is not necessarily a result from greater carbon content, because at the same carbon content, these soils can have greater cation exchange capacity. So it's something about the form, the property of biochar, not the amount of carbon per se. So that is, of course, very interesting. It turns out, and this study is from the US Midwest, where soils, mollisols, bear similar biochar type carbon from prairie burning, historic prairie burning. And not only do these soils have about half of their carbon is biochar type carbon, but this biochar type carbon is decorated with functional groups on their surfaces, such as carboxyl groups that are negatively charged that deliver this cation exchange capacity. So it is this high charge density on the surfaces of these relatively small aromatic, polyaromatic clusters that can be credited for the high cation exchange capacity. Water effects have been studied, but are much less known and investigated than some of the nutrient studies have been conducted. Here a study from Zambia, where colleagues from Norway looked at the changes in field capacity between a biochar amended conservation farming system versus a control at 5 different locations, and they looked at maize yields when in a fully fertilized system. And you can see that results vary in some areas, especially when field capacity in the controls are high. Biochar didn't do much, but if field capacity in control soils were lower, especially in sandy soils, biochar contributes significantly to field capacity, which is the ability of soils to retain water in plant available form. And at the same time, crop yields increased significantly. That wasn't the case in all sites, but in most of the studied sites, there was a significant effect of biochar. Clearly, more research needs to be done to understand fully and manage effectively water holding capacity and infiltration with biochar. Not only plants, but also microorganisms seem to benefit from biochar in soils in response to moisture stress. In this study, an elite strain of Seat 899, Rhizobia tropici, was introduced in a Western Kenyan soil that was mixed with different proportions of sand, from a very clay soil to pure sand and mixtures in between. And the Seat 899 could be isolated in nodules of a bean that was grown after a dry season simulated moisture stress. And it was telling that there was a significantly greater occupancy of this elite strain that was introduced with biochar compared to the native strain. So obviously these biochars that were in contact with, the Seat 899 that was in contact with biochar had a greater survival and a greater infection rate of the bean in the following cropping season. Global crop yield responses are instructive to get a glimpse of some of the controlling factors. They can sometimes be misleading in terms of their message of what can be achieved, because of obviously all results are reported and averaged, also those that obviously are used as contrasts. But you can see that the global yield responses in the meta-analysis that have been published, a half dozen or so, typically report that the global average response is between 11 and 28% over an unamended control. And you see there's great variation in this, whether manure is used as a biochar feedstock, a non-other crop residue, non-woody material, or woody material, whether these are field or pot studies. And without getting in too much of detail, you see great variations in there. So I would say it will be interesting to especially understand the individual responses rather than the global averages, and figure out what makes some of these responses be extremely positive as well as extremely negative. That can be very instructive. However, these are global responses, and I'll get back to that later. Some of the main factors that go into these global responses seem to be especially soil pH and soil CC. So with low soil pH and low soil cation exchange capacity, the crop yield responses seem to be the greatest, and then everything else is sort of relatively similar, with feedstock being remarkably low in the ranking, and interestingly also in this analysis biochar pH. And I'll get back to that a little later. Some of the intrigue from the Terra Preta soils, the motivation was that there was this lasting effect, this long-term lasting effect of biochar additions, and you can see here the investigation of a 3-time application over 2 years, shown in a reddish color here, and the crop yield responses, in this case maize, in a experiment on a degradation gradient. And this I'm showing here soils that have come out of forest within 10 years that have not been degraded to a large extent. And you see here comparisons between Tithonia, which leads the way. This is an unfertilized result here. So from unfertilized unfertilized crops, and you can see that that the biochar had much lower yield in the unfertilized results than the fertilized over the time when biochar was added and the amendments were added. Sorry about that. And you appreciate here that the large amounts of nitrogen that is added with a legume, or in this case Tithonia, but still nitrogen rich mulch material is more effective than biochar, where no nutrients are added except for minor amounts of phosphorus and potassium, but no nitrogen added. But you see, once the organic amendments cease, and over the next 6 years, Tithonia yields go down dramatically because it is mineralized, and the nitrogen is either leached, lost by gaseous pathways, or the carbon decomposed. Whereas some of the more persistent organic amendments, such as biochar, show a greater crop yield over the long term. These results are not enough to convince us that this is emulating these long-term fertility results, but this is the type of experiments that we should probably be doing in the future. A criticism to the earlier meta-analysis is that they very often bulk together different treatments. In this analysis, the attempt was to disaggregate fertilizer and organic and inorganic fertilizer additions from biochar additions and their combinations. The global increase, again, was within the mean increase that we've seen from other meta-analysis before, although this meta-analysis exclusively focuses on field data, not on greenhouse data. And you see that with biochar additions compared to an unfertilized control, also biochar without any fertilizer, the increase is not significant. It's a slight increase, 7%, but it's not significant. Again, biochar typically, and the majority of data from this global analysis, there are no nutrients added, significant nutrients added with biochars. So we would not expect a significant increase. In comparison, at these same sites, adding inorganic fertilizer according to local recommendations increased crop yields by 26%. Biochar additions on top of the inorganic fertilizer increased the crop yields by 15% and the combination by 48%. So you see that, and actually, no, this is a 15% increase on already a 26% increase. And this is not, these two increases are not significantly different. So the take-home message is that biochar additions were as effective as the original fertilizer in increasing crop yields, and that's I think an important message. Back to the question of pH, and that goes a little bit also into the discussion of is biochar exclusively a technology for tropical soils or not. Biochar pH and soil pH clearly play a role, but on aggregate, an important message is lost. Again, this is just field results. These are just fertilized controls. So there shouldn't be large effects of different fertility. And you see initial soil pH of less than 6.5 and larger than 6.5. So these are high pH soils, low pH soils. At low pH soils, it didn't really matter what the pH of the biochar was. The crop yield increase was about the same, and in this case, somewhere around 18%. But it mattered for the high pH soils, but only the high pH biochars added to our high pH soils lacked a crop yield increase, and no, it's a little bit lower, but it's not significant. Whereas there was no difference between low and high pH soils when low pH biochars were added. So the notion, the blanket statement that biochar is only increasing crop yields through a pH increase and in tropical soils is not correct. So the question is really where we should look at biochar as a soil amendment, and I think we're at the stage where we can start chartering a spatial analysis of biochar utility that combines projected crop yield effects and availability of biomass and, for instance, transportation, road access, and other infrastructure information. In this case here, an example for Kenya, where suitability mapping was done. Green is high suitability for biochar, purple is low. So these are, of course, relative amounts within biochar. It's not comparing to other technologies. And you see there are dramatic differences. Some because possibly the soils might not respond immediately, possibly because no biomass is available, as in the drier areas, suitability might be lower. So those kind of analysis are starting to be possible for individual regions or entire continents to give us a start into evaluating potential and directing research and extension efforts for information gathering. I would now like to highlight, following up on the earlier presentation a month ago, that biochar obviously doesn't drop from the sky. It needs to be made from a biomass source, and it is made through pyrolysis conversion. And it creates not just biochar, but it also obviously creates all kinds of other bioproducts, energy being one of them, liquid, gaseous or thermal energy, electricity, but not only energy. Other bioproducts such as bioplastics, food flavoring, etc., can be generated. So rather than seeing a biochar as a product that comes in a box, it actually should be seen as a system that straddles different sectors and can be utilize the entry points as waste management. Do we have an environmental issue with an organic resource that requires treatment? Are we interested in the energy that is produced? And well, I will focus very little on energy because of other talks in this series. Mitigation of climate change, which I would like to talk a bit more about, and obviously the soil improvement that I already introduced. Such win-win-win-win, I'm guessing, systems have their attraction, but of course they have also their Achilles heel if all benefits need to be leveraged to make it socially and financially beneficial. And the question is, now, how many of these entry points do you need to make socially and financially beneficial so that the system is socially beneficial? Quick backpedaling to biochar properties in terms of climate change mitigation. When biomass is pyrolyzed, it forms these polyaromatic clusters, as I mentioned earlier, and with the formation of these clusters, persistence in the environment goes up. So already at 350 degrees, typically mineralization rates of that material is 10 times slower than unpyrolyzed biomass. And if we get to 600 degrees and up, we might typically add another order of magnitude. So these are large differences in decomposition rates when biomass is converted. And those material properties that can be related to projected mineralization help us in guiding management as well as greenhouse gas accounting, as has been done recently. You see on the upper left side the relationship between the H to C org ratio, where the H to C org ratios are the number of protons that are bound to carbon, is indicative for the degree of fusion of these aromatic rings. So more rings fused, there can be only less hydrogen. So it's a very convenient and relatively easy to measure parameter that guides us in evaluating how persistent a biochar might be. And typically the cutoff for what the community calls biochar is 0.7 in this scale. So above that, we typically would not call this material a biochar, but torrefied material or pristine organic matter, uncharred organic matter. So you see that the fraction of the biochar that remains after 100 years reaches above 80% for materials that have an H to C org ratio of 0.4 or lower. The relationship also works, of course, with pyrolysis temperature. As I just told you, that with higher pyrolysis temperature, we have that greater fusion of aromatic rings. And at low temperature, we have less biochar remaining after 100 years. In this data set, which is a global data set, this is 64%. Above 450 degrees, that amount, average amount, goes up to 80%. And above 600 degrees to about 89%, 90%. Here you see also in studies where it wasn't clear at what temperature they were made, if all are added together, we get to about half would remain after 100 years. But of course, there are also materials that are hardly charred at all, and there's no control on what their material properties actually is. This way of looking at biochar persistence over 100 years found now entry in the recent IPCC refinements to the 2006 IPCC guidelines for national greenhouse gas accounting. They were published late last year and are undergoing still final editing before the revisions are out. So there's now precedence to start developing methods and monitoring and projection methods for biochar persistence. And the calculation includes this permanence over 100 years, but also the conversion of biomass to biochar, which is a result of different pyrolysis or thermal decomposition conditions, either pyrolysis, gasification, shown here separately, and a factor plays, of course, also the feedstock, as you've seen in the previous talk. And the recoveries, the carbon recoveries are dramatically different from just a few percentages to nearly 80% recovery of carbon. So it's really important to recognize different technologies of conversion as well as the different feedstocks, as also talked about in the last talk. How this, in this system that is not just a material property, but has several bells and whistles attached to it, how that may create value for different farming communities will look very different. Here, an example from smallholder farming communities where cooking, wood gathering, and agricultural production was studied together here in Western Kenya, where typically wood gathering means women, largely women, have to go in forests. I think in this case it was about 6 to 8 hours per week, and cook, and all the carbon, or most of the carbon that is expended in cooking is volatilized as CO2 and other gases. Whereas in a biochar system that is linked to energy generation in the household, one would reduce wood gathering, increase residue use for such a pyrolytic stove, where the pollutants are reduced in double-digit percentages, and about 0.5 tons per hectare of biochar per year can be added to smallholder farms. That resulted in this case over an 8-year period in a significant increase of maize production. This will vary significantly with different systems and different cooking habits, and is prone to all the different constraints that improved cook stove introduction has, and so all this should be seen with this backdrop very critically. Looking at the greenhouse gas budget for 3 different projects. This comes from a World Bank study that's also already a little bit older. It's one of the few ones that have been done in these kind of systems. One in Kenya, one in Vietnam, one in Senegal. You see that for all these life cycle assessments that include all the emissions as well as the avoided emissions, the losses in soil carbon when we are removing crop residues, etc. All of them have a net negative greenhouse gas balance, here shown as a proportion of the dry matter that goes into the cook stoves or the pyrolytic conversion units. But the differences are large between the different greenhouse gas balances. And that is because different systems have different components that either reduce or increase greenhouse gases. This is an illustration of the net revenue for one of those case studies, the Kenyan case study, where under the baseline study, so no pyrolytic introduction, as a small loss in revenue, time saved increases per ton of dry matter the revenue, but you'll see that when that is dwarfed by the increase in net revenue through life cycle greenhouse gas emission reductions, assuming $19 per ton of CO2 carbon prices, and you might think that's low, or you might say that's unrealistically high. That those are assumptions that of course need to be tested, whether they hold in the future or at any given location. But what you see here also is that depending on the crop yield, net revenue, the crop yield, and the time that biochar is effective in increasing crop yield, the net revenue from crop sales dwarfs all the other revenues. And so my message from such a data set would be that we really need to make this work for farmers. There's really, I would contest that it would be missing the boat if we would only look at greenhouse gas emission reductions and the revenues that can be brought in from that. We really need, this needs to work and be cost effective on its soil productivity merits alone for these systems. On the whole of a global review, already a little bit older, there's also not much newer than that at the moment. The greenhouse gas abatement averages are also all, no, the abatement is all positive except for a couple of studies that have found negative values, but the others are all positive and widely varying. So obviously site differences matter, as we know from agriculture, always do. A slight side note on climate mitigation and carbon dioxide reductions with biochar versus the one large reduction CDR system called BECCS, bioenergy with carbon capture and storage. The difference is very obvious. With biochar, we only, in this case, I would say, generate energy from about half of the biomass, and we sequester about half of the carbon in biochar. Obviously, with BECCS, we presumably create energy from 100% of the biomass and sequester 100% of the carbon. So on that basis, BECCS will always be beneficial or both win out on both energy generated and carbon sequestered. The difference in creating value for terrestrial ecosystems is also clear. For BECCS, we will inject the CO2 and there's a potential leakage, obviously. With a biochar system, we add biochar to soil where it creates supposedly value in soil for soil productivity and other soil health benefits, but also could have or has a slow leakage over time. It's not persistent indefinitely. There are combinations possible between those two. These emissions can be recycled. But the main difference is, do we want to, where do we want our biomass to go? Do we want to convert it fully into energy, or do we want to create value locally? And that might be at some point a geopolitical discussion and a societal discussion, rather than just energy and CO2 efficiency discussion. We need to now look at the risks of those two, but what I'll gloss over that. But what we also see is that there might be a place for all of these options: bioenergy without carbon capture, a biochar system and a BECCS system. And this modeling shows that bioenergy here in green, sorry, the colors were lost here. The green is the bioenergy system is advantageous, has a positive relative net present value, and initially at a low carbon price or zero carbon price, biochar at an intermediate carbon price, and BECCS at a high carbon price, which you also could see as a forward trajectory in time, that bioenergy purely from a greenhouse gas perspective might be bioenergy advantageous now, whereas biochar in the near future and BECCS in the more distant future. When we look at those systems that actually sequester carbon in soils rather than injecting them, we might be interested in relating the system's life cycle greenhouse gas emission reductions with the actual soil carbon accrual. So how much carbon are we actually adding to soil, or is soil's carbon is increasing? And both expressed in carbon terms or in carbon equivalent terms. So the whole life cycle greenhouse gas emission reductions are in here, but expressed as carbon. And that's why there is a one-to-one line here. For crop management, you can be lower or higher than the one-to-one line. For restored wetland, it will be hard to have a system that reduces more greenhouse gas emission than it accrues carbon, because that's the main accrual. In fact, very often methane emissions increase in restored wetlands, which means systems' greenhouse gas emissions are lower than the one-to-one line compared to soil carbon accrual. Whereas it seems with biochar systems, the greenhouse gas emission reductions are always higher than the actual carbon accrual in soil. That is because there are more emission reductions in the whole system than is just delivered by the crop, the carbon increases in the soil. When we look at food production and the soil carbon accrual, so bringing it back to agriculture and food production, we might be looking at dramatic differences as well, especially with trajectories with higher soil carbon accrual on a global scale. With the restored wetland, the more carbon we accrue, probably the more land we're taking out of agriculture and restore wetlands, and we will reduce food production. With cropland management, typically, while you increase food production with more carbon in soil, although now the relationships are not all as clear at the moment as one would want them to be, but there is a slight increase in food production and crop productivity with more carbon in soil. But typically when we divert more carbon from producing food to sequestering in soils, we will on a global scale see a negative relationship. Well, we might expect a negative relationship between soil carbon accrual and food production, even though it's still positive. With biochar or other external carbon sources, we typically see an increase. But we need to make sure that we understand the trade-offs of a lateral carbon transfer in these systems. So but in principle, we might expect an increase in food production with external carbon sources. If I go to the last bubble in my Venn diagram, waste recycling, there are opportunities and needs globally, and it's not just in dairy manure in upstate New York or chicken manure in New Jersey. It is crop residues globally. Here shown some pictures from Ethiopia and Kenya. but also in cities. Here from a project of Sanergy in the slums of Nairobi, where these toilets are installed to collect feces and urine separately. And the question is, how can we recycle those nutrients sanitarily, so safely, that it benefits agriculture. And one opportunity might be conversion to biochar. And it looks at comparisons between composting such feces and pyrolysis look financially attractive. When you look at the monetary value in US dollars per ton of the amendment, the compost, at least in this example, had a relatively lower value, both in terms of some of their nutrients as well as comparison with agronomic comparable materials than biochar, and the value increased with greater pyrolysis temperature, largely because of nutrient accrual. But a big problem is, of course, most of the nitrogen remains in urine, in our excreta. And how do we get this very dilute material? Although there's up to 90% of nitrogen is in the urine compared to feces, how do we get it out of there? And there are many different opportunities. Struvite precipitation is one. There are other opportunities, biological opportunities. We were looking at figuring out whether we can retain the urine nitrogen onto our charred feces. And you see that while we had some moderate success, the nitrogen content of the feces was, charred feces was 3.3 before exposure to the urine, and it was 4.47 after. So that's already a nice increase, but it's not efficient enough to recycle nutrients fully. Another attempt that might prove promising is to adsorb gaseous nitrogen, ammonia nitrogen, to these feces, and that works when first priming the nitrogen-rich chars with carbon dioxide, and then absorbing ammonia on top. And you can do this several times. It's like an onion system that packs nitrogen and carbon dioxide onto the surfaces. Those, while increasing again over the liquid system, the nitrogen content of the resultant char, also not yet shown to retain sufficient in this pilot project to make this industrially attractive. So there's still work to be done, and this is shouldn't be the only one. There should be still precipitation reactions, filtration, biological recovery that all need to be explored. But this is, of course, a large flux of nitrogen and phosphorus that we need to get out of urban systems for waste management purposes, and we need to find ways towards a circular economy to get it into our agricultural systems. Ammonia gas losses are not only a problem or an opportunity in industrial recovery and in storage or composting, but also in an agricultural field. And similar to the ammonia capture in this engineered system that I just showed, it appears that ammonia retention also occurs in agricultural field when biochar is added. Here you see results that are relative to the control, where no biochar, in this case, no biochar, no tithonia was added. When we add more tithonia, ammonia emissions increase. Here, almost a doubling of ammonia emissions. and those persist over time. This is shown over 3 years. Whereas with biochar, without tithonia, but also with moderate tithonia additions, ammonia emissions are going down on average by about 50%. Those effects seem to diminish over time, here shown over 3 years, and we don't know whether this is an asymptote or whether there will be no emission reductions over further years. So again, some food for future exploration. Phosphorus is a different beast. It's obviously, there's no gas phase to speak of, which makes things a little bit easier in recovery. And the potential seems to be also large. Here, just an example for slaughterhouse wastes. Bones and other remains from slaughtered animals, here shown for the country of Ethiopia. And it seems that that per year, if we were able, so this is just a back of the envelope calculation, if we were just able to return all the phosphorus from slaughtered animals for food to agriculture, we would put back 17 to 36,000 tons of phosphorus per year in Ethiopia, which is about 30 to 60% of the national import, or a value of $50 to $100 million per year. Now, it's not easy to return those, both to collect and to convert, and so those are really just an initial incentive to look at this a little bit harder. What makes this also, apart from just the sheer numbers of a potential, sort of a biophysical potential, interesting, is also the form that the phosphorus is in. So not just the amounts, but also the form. Amounts, again, the phosphorus contents of these bone chars are between around 10 to 15%, which compares favorably with rock phosphate or triple superphosphate. But the forms of phosphorus are really interesting. With greater crystallinity and higher charring, the zero value here being for uncharred bone meal, and this for higher temperature chars, using NEXAF's spectroscopy, so these are X-ray spectroscopy results. The crystallinity goes up with temperature, and it seems that the water solubility goes down to almost zero, so it's less movable, but the formic acid phosphorus content goes up as a proportion of total phosphorus. So we're making better plant available phosphorus out of a less plant available phosphorus while reducing mobility. So that seems to be an interesting nutrient management trait of such a transformed. So both the amounts as well as the form seem to attractive to look at that. Let's look a little bit at some preliminary data that how would we be able to collect and convert this material? Is there any chance to make this feasible? And while I wouldn't proffer any fast conclusions on this, when we tried this out in Western Ethiopia, we were able to collect more bones than we were able to process. So we exceeded our expectations at a very low price. We don't know how long that would last. So the conclusions are really limited, but promising to repeat these kind of studies in more locations. When we did a soup to nuts experimentation, so this was not just a modeling, this was actual experimentation. We built a pyrolysis unit, we hired staff to make it, we paid the collectors for their bones, and we converted it. And we came up with lower costs of our bone char that we made than triple superphosphate equivalents or diammonium phosphate equivalents under different cost scenarios. So that looks interesting to follow up on. Equally, when we conducted willingness to pay studies, for this char. It seemed that the bone char was nearly and not significantly different in experimental auctions attracted farmers as the BAP that they were used to. So the statement that bone char products or these kind of recycled nutrient products don't find a marketplace is likely not true. Again, this is just food for further experimentation rather than a fast conclusion. Sort of last points that I would like to make is that, that the spatial distribution, as I mentioned earlier, the spatial distribution of biochar needs is probably different because of soil or resources, but also the production in the case of bones or human feces. Now these are certain points in the landscape. In this case, with this example, I'm giving an example for Georgia in the US and poultry litter production. And you see on the right side in blue that poultry litter production in different counties in the state of Georgia is dramatically different. In some there's nothing produced, in some there's a lot produced. And in all likelihood, the same will be true for many other feedstocks, that the production of the feedstock is in different locations than the demand. And you can see this very clearly here. Now there's the high poultry litter production counties are actually never the one where the highest biochar phosphorus demand is. And the highest phosphorus demand is down here where there's very little poultry production in the area. So questions are now, how do we prioritize these reshuffling? How do we get to a circular economy that involves agriculture, especially with phosphorus as a limiting resource? How do we prioritize our different environmental and economic criteria? And here I'm modeling under different priorities, either environmental and sustainability versus profitability, and you get different answers. Here shown for emission reductions on the x-axis and profit on the y-axis, and you can imagine different scenarios. One that maximizes sustainability but is not interested in profit at all, or one that maximizes profit but obviously has very little greenhouse gas emission reductions, and everything in between. So you can start getting a feeling for the different priorities and make informed decisions about where do you want to be, and that will necessitate different installations. Then you would convert this poultry litter here and maybe transport here, and then the biochar would go from here to these counties where the phosphorus is needed, but not to other counties. These solutions, and solution B is shown here, have different profitability and greenhouse gas emission reduction. So those are important decisions to be made. So just the last slide, take-home messages. There is a statistically significant yield increase in global field studies in these analyses. It varies widely, but the comparisons are important. And I think we're now seeing and starting to appreciate that biochar increases of crop yield are in the order of magnitude of what fertilizer delivers in the first place. But there are big spatial and soil differences as well as differences in the greenhouse gas spatial optimization and that I just showed. So that is, of course, now there are different criteria that need to be put on this. Biochar systems can succeed with nutrient-rich feedstocks in delivering greenhouse gas benefits, but there are really still a lot of technology and industry development needed to make this technologically sound and then economically feasible. But given the need for waste management, that is a huge cost if we think about water quality in megacities. And the need for a circular economy in the future. I think this is something that needs to be done no matter how we think about about agriculture or not. There are trade-offs between food production and sea accrual, but it seems to be lower in when external carbon is added than when we accrue soil carbon with internal carbon, especially if we're thinking about set-asides or wetland restoration, which seems to be a trade-off with food production. But there's, of course, land managers will have yield prioritizations also with different management systems. So there will be also all kinds of appropriate technologies in this space. There's no black and white either. Thank you very much, and I'm happy to take questions, and I look forward to the discussion.
Thank you very much, Johannes, for your impressive presentation. And all the idea and the inputs that you gave us, and there is a lot of food for thoughts in the future indeed. And thank you. I think your presentation is quite complementary to the one given that Dr. Chiaramonti, that is online today, gave almost 1 month ago. And I took notice of the question that arrived in the chat. And before leaving the floor to Olivier, that has raised his hands, let me just pick some question from the list. The first one, the very first one, even before you started your presentation, is how many times can you apply biochar to the same agricultural fields? There is a limit. This is what is answered by Maria Wellish, and I will add also there is a maximum rate that you can add to the soil.
There's I'm sure there's a maximum rate somewhere. When we did global modeling, we put a somewhat arbitrary cap on it. That was more a cap that was a cap motivated by feedstock production than actual biochar production in many instances. The amounts, it's a bit of an academic question, because in all likelihood for a very long time, biochar application rates will be constrained by how much biochar can you produce and how much does it cost to produce it, not by the carrying capacity of the soil. Yes, no, if you add a high pH biochar to a high pH soil, you cannot add much at all before exceeding the maximum. But I've also seen experiments that apply 200, 300 tons per hectare and still see a yield increase compared to adding half of that. So giving a blanket response is impossible for that. It would need to be a very specific response. But in all likelihood, the economics constrain you from adding much at all. In fact, most of the efforts are now going towards adding as little as possible because of the costs involved at this point. This could be different if there is a market incentive for carbon sequestration and greenhouse gas emission reductions with biochar. And so we need to think about it for sure. But at the moment, that is more academic.
Thank you. Thank you. So different questions are highlighted. Are about the effect, the impact, let's say, of the feedstock that you use and the biochar that you obtain, and also if, for instance, in the suitability maps, the one that you showed in your presentation is based only on the potential agricultural yield increase. So can you somehow link the type of feedstock used, for instance, also the type of essence or wood essence used, to the type of effect on agricultural yields. And in the map that you showed, there is some other information that inside, or only agricultural yield increase, the potential about agricultural yield?
Yeah, so in this one, it's really about phosphorus, and no other crop yield constraint was considered, although I'm sure that there are a lot of soils in Georgia that would improve, where crop yield would improve by carbon additions, but we didn't even consider that because it's much more difficult to model than simply phosphorus additions, for which there are enough data. But you're right, the continental data that I showed here are, and this is just based on soil properties, whereas this example is based on soil properties and biomass availability and infrastructure. So now those will give different answers, and here the global data set was used where I showed, I think, here the effect size. So what weights the most in there is soil pH and soil cation exchange capacity in terms of suitability of biochars. But all these others were also considered in making this map, this particular map. But in this particular map, infrastructure and biomass was not considered. So that would definitely, but that's a larger project. I'm showing this to give a teaser of what's possible already, and I think FAO would be a great place to conduct these continental or global scale analysis, because I think the data are there to do it. We just need to start doing it.
Thank you. Indeed, we need to recap all the information and data that are already available. Thank you. Just if you can clarify another aspect, that is this debate about energy versus carbon capture and storage, about which you have already told us something. What do you think, and how can we modulate, let's say, this equilibrium on dependence of the context in which we would like to, we want to play a role, let's say? Do you think that there is a possibility to modulate this energy versus carbon capture and storage?
Energy and carbon capture and storage. There is a trade-off very clearly, not just between different approaches, say combustion, and then CO2 capture could be put on that as in a BECCS proposal, or you're thermally converting a little bit more of the biomass to gases and liquids and energy, and less to biochar. There's a direct inverse relationship between those. So either you're making more energy or you're sequestering more carbon. The greenhouse gas balances are not that different. So there's a difference between the greenhouse gas balance and carbon sequestration or carbon dioxide removal, CDR. And they are not that different. Yes, when you make more energy, you're sequestering and removing less carbon dioxide, but you're also making more energy that could offset fossil fuels. So if there's a fossil fuel offset mechanism possible, then the relation or the trade-off between energy and carbon sequestration is not there with respect to greenhouse gas emissions, but it is there with respect to carbon sequestration. So then of course we are putting less into a soil, we're improving fewer soils, we're removing more carbon from the landscape. Yes, we're offsetting more fossil fuels, but we are also withdrawing organic carbon from agricultural watersheds. And that is that's I would almost say that's as I said earlier with the BECCS versus biochar discussion, it's more a geopolitical and maybe socio-political discussion. What is has more value to us, carbon in soil and in agricultural systems, or more fossil fuel offsets? And that is a big and important discussion that we need to lead.
It depends also on the place in which we want to propose biochar, or for instance, gasification for energy production. Where it replace, for instance, wood fuel, and so it reduces the emissions compared to a traditional tree stone fire. So it depends also, as far as I understand, from the business as usual that we are going to replace by introducing biochar for energy production and as an agricultural amendment. But can you explain which are the limits of biochar? Because you have done so many activities in sub-Saharan Africa, and which have been the most important challenges that you have encountered in many years. How many years, how long did you, are you working on biochar in Africa? So since many years ago, so which are the major challenges that you have encountered in this period?
Of course, too numerous to recount and remember even. I think I started in South America in the late 90s when we started our first biochar trials, adding biochar in soil, inspired by terra preta. But we started in the mid 2000s adding char coal in Kenya, our first site where we started that. And I have done that now in half a dozen countries across sub-Saharan Africa. Now, looking at it from a systems view is absolutely necessary. And even though one part of the system might work well, let's say we find a biochar that mitigates a very important crop and soil constraint at a certain location. But there's no way of making that biochar because the feedstock is not around, or the feedstock is around, but there's no conversion, or it's not economically feasible. Or there's nobody interested in doing that. There's so many parts where this can break down. And as I said, when I showed the Venn diagram, the strength of these systems that are potential win-wins or multiple wins can also be their drawback. That if you have to leverage all these benefits to make it financially viable, it's much more difficult. If you have to get carbon credits and mitigate climate change, if you have to use a waste feedstock and you have to increase crop yields, that this all comes together makes it very attractive, but also challenging in a way. And mapping it onto a landscape and a heterogeneous landscape is not easy. What's also challenging is the multiple opportunities. Now there are innumerable types of feedstocks. There are really also still an expanding list of soil and crop constraints that might be mitigated with a certain biochar or another. Mapping that onto a very heterogeneous landscape and social and financial and economic structure is challenging to hit everything right. So I think while we have enough data and experience and results for making some safe bet recommendations, obviously for having a hit-all decision tree, we're necessarily very far away. But maybe that's also not necessary to have at this juncture. But that's sometimes the debate that is inevitable, but hopefully not a condition.
Thank you, Johannes. I hope we can have the opportunity to forward to you some more questions, because there are so many in the chat, and I would like to give the floor to Olivier Dubois, and that raised his hands. Please, Olivier, if you can unmute your microphone, maybe. Okay, thank you. Please go ahead.
Fascinating presentation. I'm a soil scientist, so I'm fascinating anyway. But I mean, you answered a bit my question in a way. This biochar is not a silver bullet, and almost you need to assess the feasibility in a systematic way, and it depends on the context. So the question becomes, what would be the key 2 or 3 things to do to further this discussion on the pros and cons of biochar? Because I'm happy to hear that you say it's not a silver bullet, because many people might be over optimistic about the benefits of biochar without looking at the drawbacks. And so, in your view, what would be the 2 or 3 key actions? You say we have enough data, but if we want to go to the farmers, do we need what do we need? Do we need just to try with them? Do we have a low-hanging fruit? You know, no regret pathways, stuff that can help move forward with biochar.
Yeah, no, that's a good question. Thank you, Olivier, for that. No, I absolutely agree. Biochar is not a silver bullet. Now, cars are good for driving, but not good for flying. You know, there are places for technology and things they cannot deliver, and all of them have some drawbacks. I think what some of our colleagues are doing very well, and your FAO colleagues, is a participatory research development and research design, and I think putting biochar as one option in the basket of options is probably the way to do it. And it needs to stack up against the other options that farmers have, be it changing tillage, new germplasm, fertilizers, lime, composting, crop residue return, you name it. What makes it a bit more challenging at this juncture is because there's less information in the public domain. It's still more in the realm of experts and science, and there's less experience, not the least with farmers. Farmers are aware of what DAP is, and they've seen it, even if they can't afford it, and they might not even have never heard about biochar. So there are quite a few layers of challenges. But we've seen that with other technologies. No-till was nowhere to be seen in the 50s and 60s, and even in the 80s, U.S. farmers have said, "Oh, no-till, this is good for Brazil, but it's not for U.S." And now 20 years later, the landscape has changed. So I think, and still, no-till is not for everyone. There are strengths and weaknesses and locations and their costs and drawbacks and trade-offs. And that will be the same for, or is the same for biochar. Where it adds value that other technologies cannot at a certain location, that might change with location and access to technology and knowledge and time will change all of that. we need to recognize all of that. But it's I would agree with you if you said, and you might imply that that we need to start putting it into the basket and generate these on-farm experience and document them appropriately, as we do for other technologies.
Okay. Thank you.
Thank you.
Thank you very much. Indeed, we in Italy have not till since the last decades, probably, or 20 years, no more than that. Even in our 20-hectare farms. But let's go ahead. I'm sorry, but this is a debate and this discussion is very interesting, and but that our time is gone, is expired, let's say, and we will try to collect all the other questions from participants, and we'll forward them to you if you can briefly answer them. And nothing, let me give the floor to Michela for the closure remarks, and thanks again. Thank you very much, Johannes. I look forward to our next opportunity to having you as a speaker to collaborate with you. Thank you, and Michela, the floor is yours.
Very much, Tiziana, and thank you very much, Johannes. Really, your presentation has been extremely fascinating and inspiring, and we've learned a lot in terms of how much still needs to be done. But it's also true that there are potentials, a lot of potentials behind biochar, and the important thing is try to be active and proactive now to test into the field, into concrete situations, how biochar could provide positive feedback. For sure, biochar will have a role to play in the context of sustainable development goals in terms of climate targets, and you stated very clearly in terms of opportunities and potential impact. And in particular for agriculture in terms of increased yield. So we do see a lot of positive win-win-win-win, as you said. But of course, it's important to start very concrete activities in the countries in order to also to analyze the challenges and face the challenges in light of the geographical circumstances of the activities themselves. So thank you, Johannes. Thank you, Tiziana and Connie, for the support for this webinar. And thank you all to all the participants for their interest. Of course, this webinar is recorded, and the link to the recording will be posted on the GBEP website very soon, together with the PowerPoint presentation that Johannes just gave us. Thank you so much. Have a good rest of the day to you all. Bye.
Bye.
Bye. Thank you.
Bye.